Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below. I want you to, I want you to start off today by picturing a massive Roman siege engine.
Oh, wow. Starting with the heavy artillery.
Right. Like, think of one of those towering, terrifying timber beasts built, 2,000 years ago. It's just groaning under immense tension. The air is thick with the smell of pine and sweat. And you've got these thick ropes made of braided animal sinew, just twisted to their absolute breaking point.
Yeah, just massive amounts of potential energy waiting to unleash.
Exactly. And then suddenly a release pin is knocked loose, and the machine hurls this massive boulder through the air with enough kinetic energy to completely crush a solid stone wall to dust.
It's terrifying to even imagine being on the receiving end of that.
It really is. So got that image in your head, the sheer, unadulterated violence of it. Okay, now I want you to wipe that slate completely clean and picture something entirely different. Picture the delicate, sweeping, perfectly timed motion of a windshield wiper clearing the rain off your car on a stormy night.
Which is, a very different vibe.
Totally different vibe. It goes up, it stops, it reverses, it glides back down.
Yeah.
Over and over with this absolute, almost hypnotic consistency. Now, on the surface, these two things seem worlds apart, like they belong to completely different universes of engineering and human thought. But they are deeply, intimately connected through this incredible, often hidden history of kinematics.
Which is, at its core, the geometry of motion. It is the invisible underlying math that dictates exactly how things are allowed to move in the physical world.
Right.
It's the framework that governs everything from, how a pair of scissors opens to how the landing gear on a massive commercial airliner folds itself up into the fuselage.
And that is our mission for this deep dive. We are going on a journey through the evolution of mechanical design. We're going to explore the critical and honestly kind of mind-blowing distinction between raw force and precise motion. We'll trace the surprising history of ancient automata and odometers in the streets of ancient Egypt.
Yeah, that's one of my favorite parts of the history.
It's so good. And we will debunk a massive myth about the so-called Dark Ages. And ultimately, we are going to unpack the 6 fundamental building blocks of all machinery. And it all culminates in what I genuinely think is some of the most beautiful, chaotic mathematics in the entire discipline of engineering, the 4-bar linkage.
It's a really fascinating trajectory to follow, mainly because the way we conceptualize engineering today, as this precise mathematical control of space and time, it's entirely different from how the ancients thought about it.
Oh, completely.
Yeah, to really grasp kinematics and to understand why it took humanity thousands of years to master it, we really have to start by pulling apart 2 words that people use interchangeably all the time today. But historically and conceptually, they have vastly different meanings.
Okay, what are the words?
Those 2 words are machine and mechanism.
Oh, yeah. I'm guilty of this immediately. I definitely use those words like they mean the exact same thing. Like, if I look at a car engine, I'll call it a machine in one sentence and a mechanism in the next without even thinking about it.
Oh, the majority of people do. And I mean, in colloquial speech, it doesn't really matter. But if we go back through the historical record, the concept of a machine is heavily, almost exclusively, associated with the use and transformation of force.
So it's about power.
Exactly. It is
Right.
fundamentally about brute strength. When early engineers, the pioneers of antiquity, talked about machines, the goal was almost always moving extremely heavy weights.
Right, like building the pyramids.
Yeah. Think about the logistical nightmare of building the Egyptian pyramids or erecting massive stone monuments in Greece. Or, going back to your opening visual of the siege engine, think about Archimedes defending the city of Syracuse from the Roman Republic between 214 and 212 BC.
Syracuse is a great example because he built these terrifying defensive structures, right? Like
Yeah.
the famous Claw of Archimedes.
Yes, the claw is the perfect embodiment of an ancient machine. So Roman warships would sail up to the seawalls of the city, and Archimedes had designed these massive cranes equipped with grappling hooks.
It's like something out of a movie.
It really is. The hook would be lowered down, it would bite into the wooden hull of the Roman ship, and then using a massive system of pulleys and levers operated by oxen or crowds of soldiers, the crane would literally lift the prow of the ship completely out of the water.
Wow.
And then suddenly they drop it, causing the ship to capsize or swamp. That is a machine. Its entire purpose, its entire reason for existing is the multiplication of force.
It's about sheer muscle, just magnified. It's taking the pulling power of 10 men and turning it into the pulling power of 1,000 men.
Right. But a mechanism is a completely different philosophy. When you hear the word mechanism, it should conjure up the idea of motion, pure directed motion.
Okay, so less about force, more about the path.
Exactly. Now, obviously, forces still exist in a mechanism. You can't have motion in the physical universe without some kind of force initiating it, but the force is entirely secondary. The primary goal of a mechanism is the exploitation, the geometric control of precise movement.
Okay, let me try an analogy here to see if I'm tracking the difference. It's like the difference between an industrial hydraulic press and a mechanical Swiss watch.
Oh, I like that.
Yeah, like both of them live in the same broad body of engineering. They both obey the exact same laws of physics and thermodynamics, but one is a bodybuilder and the other is a ballerina.
The bodybuilder and the ballerina, that is a phenomenal way to visualize it.
Right, because the hydraulic press just pushes with this crushing downward force. It doesn't need to trace a complex path in three-dimensional space. It just needs to go down hard. But the Swiss watch, on the other hand, isn't trying to crush anything. It barely has any torque at all.
Right. If you put a watch under a press, it's game over.
Exactly. Its entire existence is dedicated to moving its tiny hands in a perfectly calibrated, endlessly repeatable geometric path.
And for centuries, millennia, really engineering was almost exclusively focused on the bodybuilder aspect. If you read the surviving texts from antiquity, this bias is overwhelmingly clear.
They were just obsessed with lifting heavy stuff.
Pretty much. Take Vitruvius, the Roman architect and military engineer who wrote extensively around 28 BC. His definition of a machine, translated from his text, was purely, and this is a quote, a combination of timber fastened together, chiefly efficacious in moving great weights.
That's it, timber and heavyweights.
That was the boundary of his engineering imagination. It was entirely centered around civic construction and warfare. And then a bit later, in the 1st century AD, you have Hero of Alexandria, who famously defined what we now call the 5 simple machines.
Right, the classic building blocks we all learn about in elementary school science class. The lever, the windlass, the screw, the wedge, and the pulley.
Yeah, but take a close look at how Hero defined those 5 tools. He didn't define them as methods to alter or control the complex path of an object in space. He defined them entirely around moving a given weight by a given force.
So again, it's just about mechanical advantage.
Exactly. Lever lets you lift a heavy rock with less downward push. A wedge lets you split a heavy log with a hammer strike. A pulley lets you hoist a heavy sail. It was all about the mathematics of lifting rocks and breaking walls.
So for a remarkably long stretch of human history, the narrative of engineering is essentially just humans trying to figure out how to lift heavier and heavier rocks with less and less back pain. That feels, I don't know, surprisingly primitive for how advanced we know the Romans and Greeks were.
It does seem that way, right? If we only look at their public works, absolutely. But while the ancients were publicly obsessed with force for construction and military dominance, they also had a secret, highly sophisticated, playful side.
Oh, I love this part.
Yeah, it was out of this playful side, this sandbox of curiosity, that the first true mechanisms, the ballerinas, to use your analogy, were born.
I really love this transition because when most of us think of ancient technology, our minds immediately go to the massive aqueducts spanning valleys or the catapults. We think of heavy masonry. But if we travel to Alexandria in Egypt around the 3rd century BC, we find what was essentially the ultimate ancient hub of science and technology. It was like the Silicon Valley of the ancient world.
It really was. Under the rule of the Ptolemies, Greek science, philosophy, and technology were nurtured in Alexandria to an astonishing degree. This is the city of the Great Library, the Museum.
All the heavy hitters were there.
Oh, yeah. This is where Euclid was systematically writing his elements of geometry, laying down mathematical laws we still use today. It was an environment just flush with resources, brilliant minds, and crucially, cross-pollination of ideas from across the Mediterranean and the Middle East.
And it's here in Alexandria, amidst all these scrolls and scholars, that engineers started developing incredibly complex mechanisms. And they weren't building them for heavy lifting. They were building them for things like data tracking and public spectacle.
Yeah, which is fascinating.
Let's talk about the odometer, because this absolutely blew my mind when I was reading through our sources for this deep dive. We have a detailed description, again from Vitruvius, of an odometer designed by a Greek engineer and mathematician named Ctesibius.
Ctesibius is a towering figure in early mechanics. He's often considered the father of pneumatics, but his work in gearing and instrumentation is just as vital.
So imagine you are a Roman surveyor, right? Or a wealthy merchant, and you need to measure distances along this vast network of Roman roads. You would attach this device, this odometer, to your horse-drawn carriage. The device featured a very specific carriage wheel that rolled along the ground. That wheel was exactly 4 feet in diameter.
Which is not an arbitrary size. It is a very specific, mathematically chosen dimension tailored for the Roman measurement system.
Completely deliberate. Because if you have a wheel with a 4-foot diameter, simple geometry tells us its circumference is roughly 12.5 feet. So inside this ancient wooden odometer box mounted on the carriage, there was a complex gear train. And the primary gear in this train had exactly 400 individual teeth.
Yeah, the precision is wild.
It is. As the 4-foot carriage wheel turned along the dirt road, a peg on its axle engaged this massive gear system inside the box.
Just think about the mechanical implications of that for a second. If the carriage wheel has a circumference of 12.5 feet, and it takes 400 revolutions of that wheel to turn the internal gear, exactly one full rotation, well, 12.5 multiplied by 400 equals exactly 5,000 feet of continuous travel along the road.
And 5,000 feet was exactly 1 Roman mile.
Exactly.
Let's just pause and appreciate that for a second. The sheer, excruciating precision required to cut a 400-tooth gear by hand out of bronze or hardwood in the ancient world. If one tooth is slightly too thick, the gear binds. If one tooth is too thin, the gear slips, and your measurement is completely ruined.
Right, there's zero margin for error.
The craftsmanship alone is staggering. But what I love the absolute most about this device is the user experience design, like the UX of antiquity.
Because they had a very real constraint. They didn't have a glowing digital dashboard or a visual dial with a needle for the driver to stare at.
Exactly. If you are driving a team of horses over a bumpy, unpaved road, looking down at a tiny dial to read your mileage is incredibly dangerous. You have to keep your eyes on the road. So, Ctesibius and these engineers came up with a brilliant solution. The top gear in this mechanism laid flat horizontally, and it had holes drilled near its edge.
Right, around the perimeter.
Yeah, and inside each hole rested a small round stone, a pebble. Every time that primary gear completed one full revolution, meaning you had traveled exactly 1 Roman mile, one of those holes would align perfectly with a hollow tube leading out the bottom of the box. Gravity would take over, and a single stone would drop through.
And it didn't just drop onto the dirt road where it would be lost, and it didn't drop into a soft leather sack where it would make no sound. It fell into a specifically tuned bronze vessel acting as a resonator.
Yes, it made this loud, sharp, unmistakable ringing sound. So the passengers in the back and the driver managing the horses knew a mile had just passed without ever having to avert their gaze. It was an ancient audio feedback interface.
It really was.
It's basically the ancient equivalent of your smartwatch pinging your wrist when you hit your 10,000-step goal for the day.
Look at the underlying philosophy of that device, though. This is a pure mechanism. It's not moving a heavy weight.
Yeah.
It's not destroying a siege wall. The physical forces involved are microscopic. Just the friction of small grease gears turning against each other and the tiny gravitational force of a pebble dropping.
Right, it's delicate.
The entire purpose, the soul of the device, is the geometry of motion. It is taking continuous linear motion, the carriage moving along the road, translating it into continuous rotary motion of a wheel, stepping that motion down through a high-ratio mathematical gear reduction and converting it into a periodic, intermittent physical output, the dropping of the stone. It is an absolute masterpiece of kinematic thought.
And odometers weren't even the most theatrical things they were building. The sources talk about what were essentially ancient programmable robots.
Oh, the temple automata. Yeah. Hero of Alexandria, who we mentioned earlier regarding the simple machines, wrote entire treatises on these. They were essentially mechanical special effects.
The sources describe these incredibly elaborate setups where Hero would use a combination of pneumatics, thermodynamics, and hidden mechanics to create literal magic for the masses gathering at the temples.
Pure spectacle.
Right, so picture this. You have a massive, imposing stone temple. In front of the heavy, closed temple doors, there's a sacrificial altar. The high priest walks out, chants an invocation, and lights a fire on the altar.
To the crowd, this is a purely spiritual act.
Yeah.
But below the stone floor, it is a thermodynamic engine.
Right, because the altar is hollow, and a metal tube runs from the altar down into a hidden subterranean chamber. In that chamber is a large spherical vessel partially filled with water. As the fire on the altar burns, it heats the metal, which heats the air inside the hollow altar and the tube.
We know from basic physics that hot air expands.
Exactly. This expanding hot air pushes down on the water inside the hidden vessel. The water has nowhere to go but up and out through a siphon tube, which pours the liquid into a hanging bucket.
And this is where the pneumatics hand off to the mechanics.
Yes. This bucket is suspended by a complex series of ropes and pulleys. These ropes are wrapped carefully around the subterranean spindles, or the pivot posts, of the massive temple doors above. As the bucket slowly fills with water displaced by the hot air, it gets heavier and heavier. Eventually, the weight of the water bucket is enough to overcome the friction of the heavy doors. The bucket sinks, the ropes pull, the spindles rotate.
And so, to the awestruck crowd standing outside in the sunlight, the priest lights a holy fire, and moments later, smoothly and entirely on their own, these massive, impossibly heavy temple doors magically swing inward to reveal the statue of the god inside.
It's just unbelievable.
And when the fire burns out, the air cools, creates a vacuum, sucks the water back out of the bucket, and counterweights swing the doors shut again.
It's theatrical engineering. It's an animatronic show at an ancient theme park. But, reading about this, it genuinely made me frustrated.
Yeah.
Because it makes you wonder, if they had this level of sophisticated mechanics, they understood complex gear trains, they understood pneumatics, they had valves, siphons, regulators, why didn't they use it to kickstart an industrial revolution right then and there?
It's a fair question.
Like, why didn't they attach that heat engine to a loom or a mill instead of just using it to trick peasants at a temple?
That is the great historical what if. But to understand why the Industrial Revolution didn't happen in 3rd century BC Alexandria, we have to look past the engineering and look at the socioeconomic reality of the time.
Okay, so it wasn't a technology problem.
No, it comes down to the brutal economics of capital and labor. Ancient research and development required vast amounts of funding, just like modern R&D. And without a modern venture capital system or a culture of mass consumer patents, R&D was funded by two primary state-sponsored sources.
The military, I'm guessing.
First, the military, which demanded siege engines and weapons, and second, religion and civic entertainment, which demanded awe-inspiring spectacles to maintain social order and religious authority.
So there wasn't a middle-class consumer market to buy labor-saving devices?
More importantly, there was no economic incentive to save labor at all, because the Roman Empire and the ancient Mediterranean at large ran on a massive, institutionalized slave population.
Ah, right. The dark reality behind the classical world.
Yeah. When a society has access to virtually unlimited, brutally cheap human muscle power, the wealthy elite have zero economic incentive to spend fortunes developing labor-saving production machinery.
I guess that makes dark economic sense.
Why spend a decade and tons of expensive bronze trying to invent a complex mechanical grain mill when you could just purchase 50 enslaved humans to push a heavy grinding stone in a circle all day? Muscle power, tragically, was the engine of the Roman Empire. So these brilliant mechanisms, the odometers, the automatic doors, the mechanical singing birds, they remained playthings. They were novelties and magical tricks for the rich and the religious, rather than the foundational engines of industry.
Which brings us to a massive historical pivot point in our deep dive. Because eventually, the Western Roman Empire collapses, and we usually hear about what happens next, described in pop history as the Dark Ages.
Oh, yes.
This idea that Rome fell, the barbarians took over, and science, mathematics, and technology just completely died for 500 years until the Renaissance magically woke everyone up.
That is one of the most persistent and frustrating myths in history. And from an engineering perspective, it is completely inaccurate. Following the collapse of the Western Roman Empire in the 5th century, science didn't die at all. The center of gravity simply shifted.
Right.
It moved east to the Byzantine Empire in Constantinople, and particularly to the Arab world during the Islamic Golden Age, beginning in the 7th and 8th centuries.
So the knowledge wasn't lost, it just relocated.
Exactly. Arab and Persian engineers and polymaths preserved the Greek and Alexandrian texts. They translated them. But they didn't just act as passive librarians hoarding old scrolls. They dramatically improved upon those mechanics.
Oh, definitely.
Engineers like the Banu Musa brothers and later Al-Jazari were building incredibly complex water clocks that featured programmable mechanical musicians, intricate planetary models, and geared mechanisms that far surpassed anything Hero of Alexandria had built.
But even back in Europe, if we look at the period between roughly 500 and 1000 AD, things were slowly changing in a way that would fundamentally alter the course of mechanics. The socioeconomic structure of Europe underwent a massive foundational shift.
Yeah, the old Roman system just fell apart completely.
Exactly. The central authority, The massive logistical supply chains and vast agricultural estates worked by thousands of slaves, it all disappeared.
And nature abhors a vacuum. In its place, a new societal structure grew.
Right, you had the rise of feudalism, but you also had the rise of new agricultural methods. Things like the heavy plow, which allowed them to farm the dense soils of northern Europe. This led to a surplus of food, which eventually led to urbanization, and the rise of a brand new class of independent artisans, blacksmiths, and merchants.
Absolutely. And this shift in the labor force raises the most important question of medieval engineering. If these local artisans and village blacksmiths weren't building giant Roman aqueducts or massive colosseums, what were they actually building?
Well, they certainly aren't lifting giant marble blocks anymore to build temples to Jupiter.
No, they were building industry. Because without the massive Roman slave labor force, these new, decentralized European societies had to look elsewhere for the power to produce goods. Human labor was suddenly much more valuable. And so this era saw an absolute explosion in the use of what they called natural powers, specifically, harnessing the kinetic energy of wind and water.
So we are talking about the iconic medieval water wheel and the windmill. You see them in every fantasy movie sitting quaintly next to a river. But, kinetically speaking, they represented a huge problem, didn't they?
A massive problem. Here is the critical engineering leap that occurred during the medieval period. A water wheel sitting in a flowing river gives you continuous rotary motion. The river flows in a straight line, the wheel spins in a circle.
Which is fine for some things.
Right, that is great if all you want to do is turn a circular grinding stone to make flour. But to do complex industrial work like sawing wood for building or operating heavy trip hammers for forging iron or pounding cloth in a fulling mill, you rarely need simple continuous rotary motion. You need complex reciprocating motion.
Wait, I want to make sure I'm visualizing this correctly. You have a massive wooden wheel spinning endlessly in one direction because the river never stops. But for a blacksmith's hammer, you need a heavy anvil and a hammer that lifts straight up into the air, stops, and drops violently back down, over and over.
Exactly. You need up and down motion, but your power source only provides round and round motion. And you cannot bridge that gap with just brute force. You can't just attach the hammer directly to the wheel. You need a mechanism.
All right, you need something in between.
You need a kinematic linkage that can physically translate one type of motion into a completely different type of motion.
So how did they actually achieve this back then without modern math or like steel alloys?
The most famous and perhaps most revolutionary medieval solution was the cam and the trip hammer. Imagine the central wooden axle of the water wheel extending horizontally into the blacksmith shop. As the wheel turns outside, this heavy wooden log is slowly spinning inside the shop. Now the blacksmith drills a hole into the side of this spinning log and drives a sturdy wooden peg into it. That peg is rudimentary cam.
Okay, so you have a spinning log with a peg sticking out of it like a single spoke.
Now, position a heavy wooden beam, a lever perpendicular to that spinning axle. On one end of the beam is a heavy iron hammerhead resting on an anvil. The other end of the beam rests near the spinning log. As the log turns, the peg comes around and pushes down on the end of the beam.
Ah, it acts as a lever. The peg pushes down on the back of the beam, which causes the front of the beam, with the heavy hammerhead, to lift up into the air.
Precisely. And as the central log continues to rotate, the peg eventually slips off the end of the beam. The support is instantly gone, gravity takes over, and the heavy hammer crashes down onto the glowing iron on the anvil. Then the log completes another rotation, the peg comes around again, pushes the beam down, lifts the hammer, and drops it. You have successfully converted continuous rotary motion from a river into violent reciprocating vertical motion in a forge.
That is brilliant in its simplicity. But it also sounds like it was all very haphazard. It was trial and error, right? Like a blacksmith would just tinker with wooden beams and iron pins, adjusting the peg, moving the pivot point, until the hammer fell at the speed and height they wanted.
It was completely organic, random growth. There was no underlying mathematical theory guiding them. They were solving mechanical problems by intuition. This necessity for converting motion sparked a quiet revolution over the next several centuries. Medieval engineers spawned a multitude of machines with increasingly complex, weird, and wonderful mechanisms.
Right.
But for nearly 2,000 years, even as mechanisms got insanely complex during the Renaissance and into the early days of the Industrial Revolution, the world still theoretically relied on Hero's 5 simple machines from antiquity to explain how things worked.
But those 5 machines, the lever, the pulley, the wedge, they only explained the magnification of force. They were completely inadequate for explaining complex, continuous, transforming motion.
They were conceptually bankrupt when it came to motion.
It's like trying to write a complex emotional symphony, but someone tells you the only instruments that exist in the world are 5 different sizes of snare drums. You can make a lot of rhythmic noise, you can hit things really hard, but you cannot create a soaring melody. You can't sustain a note. The engineering world was building these massive, clanking, hissing, steam-driven factories in the 1800s, but they desperately needed a unifying theory of design. They needed a new alphabet for motion itself.
And that alphabet finally arrived, quite late in human history, around 1875. It came courtesy of a brilliant German mechanical engineer and kinematician named Franz Rouleau.
Rouleau, what a legend.
Truly, Rouleau was living in the height of the Industrial Revolution. He walked through these chaotic, deafening factories filled with thousands of custom-built, complicated steam engines and textile looms. He looked at the absolute mess of belts, gears, and swinging arms, and he realized that the old 5 simple machines of antiquity were dead wrong for explaining what was actually happening in front of him.
He essentially did for mechanical engineering what Dmitri Mendeleev did for chemistry. Mendeleev looked at all the messy, chaotic physical matter in the universe, the gases and metals and salts, and he realized there was an underlying logic. He organized it all into the periodic table of elements. Franz Rouleau did the exact same thing for motion.
He really did.
He looked at every machine on Earth, stripped away the fancy brass casings and the steam whistles, and proved that underneath they were all just mechanical molecules made up of 6 basic atoms. He broke down the entire mechanical genome into 6 fundamental building blocks.
He called them kinematic pairs, but building blocks is the perfect way to visualize it. And instead of just listing them out like a textbook, let's look at how we logically categorize the universe of motion, because each block solves a specific geometric problem. Rouleau started with the most basic problem. How do you connect 2 points so they move in a predictable arc?
Okay, what's the first one?
His first block is the I-bar link. Think of a rigid steel bar with a pin joint drilled through each end. Cranks and levers fall into this category. It's the most fundamental way to constrain motion. If you pin one end to a wall, the other end can only move in a perfect circle around it.
Okay, but an I-bar swinging back and forth isn't always enough. What if you need to transfer continuous rotation across a distance? You can't do that with a swinging stick. So his second block addresses that. The wheel. This includes all forms of gears and friction disks. The wheel transfers endless, continuous rotary motion from one axle to another.
But what if continuous motion is exactly what you don't want? What if you have a continuous input, like a steam engine, but you need an output that moves, then stops, then moves, then stops? This was a massive realization by Rouleau. He defined the ratchet as its own fundamental building block.
Oh, that makes sense.
Yeah, the ratchet is the physical embodiment of intermittent motion, or one-way motion. It allows the gear to turn clockwise, but a physical pawl drops into place to absolutely prevent it from turning counterclockwise.
So we have arcs, we have continuous spinning, and we have start and stop motion. But what if you need a highly specific, customized, irregular motion? That's where Rouleau's next block comes in. The cam. We talked about the wooden peg on the medieval water wheel. That was a primitive cam. But a modern cam allows you to literally store a custom motion profile in the physical shape of a spinning object.
It's like physical software.
Exactly. You carve a bumpy asymmetrical shape out of steel. A follower, a little metal rod, rides along the bumpy surface of that spinning cam. The rod moves up and down in the exact complex pattern that you carved into the metal. It is essentially an analog memory drive for motion.
Then Rouleau recognized the need to convert rotary motion into sheer linear pushing force, but with geometric precision. This gives us the screw, not a screw used as a fastener to hold wood together, but a lead screw. Think of the massive threaded rod on a machinist's lathe. As it turns, it slowly and smoothly translates that turning motion into linear motion, driving the cutting tool forward with microscopic precision.
And finally, we arrive at block number 6. I want to spend a second on this one, because when I read the source material for this deep dive, this completely threw me for a loop. It feels completely counterintuitive to everything we've talked about. Rouleau's 6th block is called tension compression organs.
I genuinely think this is Rouleau's most brilliant outside-the-box categorization. He recognized that parts possessing what he called one-way rigidity completely alter the kinematic geometry of a system.
Wait, hold on. This is where I struggled. You're saying a fluid in a rubber tube or a hemp rope counts as a mechanical geometric component just like a solid steel gear. I'm having a hard time visualizing how a sloshing liquid or a floppy rope replaces a solid metal bar in a machine.
It requires a shift in how you view physics. Think about a standard steel eye-bar. It is rigid in two directions. If you push it, it stays solid. If you pull it, it stays solid. It transfers force perfectly in both directions.
Yeah.
Now, think about a bicycle chain or a belt. A chain is entirely flexible if you push it. If you try to push a chain, it just collapses into a pile on the floor. It has zero rigidity and compression. But, and here's the key, the microsecond you pull that chain, it becomes instantly rigidly taut. It acts exactly like a solid steel bar, but only in tension.
Okay, I see. And the reverse is true for hydraulics. A fluid trapped inside a hydraulic line will push with incredible rigidity. Because liquids don't compress easily, it transfers compressive force from one end of the tube to the other perfectly. But if you try to pull a fluid, it just separates, it cavitates, it has zero rigidity and tension.
Precisely. So Rilot realized that a rope pulling or a fluid pushing bends the geometric rules of the mechanical universe. Think about the implications. You can route a rope around 3 different pulleys, navigating through the tight corners of a machine, effectively changing the direction and path of the rigid link in a way you could never ever do with a straight steel bar. By recognizing these one-way rigid elements, he completed his periodic table.
It really was a paradigm shift. By defining these 6 kinematic components, the eye-bar, the wheel, the ratchet, the cam, the screw, and the tension compression organs, Rouleau gave engineers the theoretical tools, the mathematical vocabulary, to analyze and synthesize literally any mechanism imaginable.
And once you have the vocabulary, you can start writing poetry.
Which brings us to the grand finale. We have our 6 mechanical atoms. Now, I want to zoom in on just one of them, the very first one, the eye-bar link, the simple bar with a pin at each end. Because if you take just 4 of these rigid bars and you pin them together end to end in a closed loop, you create what is arguably the most important, versatile mechanism in the entire history of human engineering.
We're talking about the 4-bar linkage.
Yes, the 4-bar linkage. It sounds so deceptively simple. 4 sticks, 4 metal pins. It sounds like something a toddler would build out of popsicle sticks. But mathematically, it is the ultimate canvas of motion.
To understand how something so simple is so powerful, we have to define the anatomy of the 4 bars. We have to understand how they interact in space.
Let's break it down.
First, you have the frame. This is the foundational bar. It is fixed to the ground or fixed to the chassis of the machine. It does not move.
It's the anchor point for the rest of the system.
Right. Attached to one end of the frame by a pin joint is the crank. The crank is almost always the input of the system. In a motorized machine, the crank is attached directly to the motor shaft, meaning it spins in a full, continuous 360-degree circle.
Okay, so the crank is spinning wildly in a circle.
Now, attached to the other end of the frame is the rocker. Based on its geometry, the rocker doesn't spin all the way around, it just oscillates. It swings back and forth in a limited arc, like a pendulum.
So we have a spinning input and a swinging output, but they aren't connected yet.
That is where the 4th bar comes in, the coupler. The coupler is the magic piece. It bridges the gap. It is pinned to the end of the moving crank on one side and pinned to the end of the moving rocker on the other side. Here is the critical piece to visualize. The coupler is not attached to the ground at all.
It's just out there.
Yeah, it is entirely floating in space, being violently whipped around, pulled by the spinning crank, and pushed by the swinging rocker simultaneously.
To give you a mental image, think of the human knee. Your femur, your thigh bone, and your tibia, your shin bone, are like the crank and the rocker. But your kneecap, the patella, isn't anchored directly to the main skeleton. It floats in a complex web of ligaments between the 2 bones. As your leg bends and straightens, the kneecap traces a very specific, complex path to provide leverage. The coupler in a 4-bar linkage is that floating kneecap.
That is an excellent biological analogy, because the path is everything. Now, here is where we dive into the beautiful, chaotic mathematics. If you are an engineer designing a machine, you don't actually care about the physical bars themselves. They are just the scaffolding.
Right.
You care about what happens to a specific invisible point sitting somewhere out on that floating coupler bar. Because as the crank spins its perfect circle and the rocker swings its simple arc, that specific point on the floating coupler travels through space, drawing an invisible, complex, closed loop in the air.
We call those invisible loops coupler curves. And the sheer variety of shapes these curves can take just by altering the lengths of the 4 sticks is staggering.
But to really appreciate this, we have to talk about how engineers use this before software. Before computers could simulate these mechanics in real time, engineers relied on massive, physical, printed books. The most famous of these was the Rones and Nelson Atlas.
The atlas is legendary. Picture a massive, heavy book, 11 by 17 inches across. You open it up, and it's literally thousands of pages of nothing but ghostly dotted line curves. Page after page of mathematical shapes showing what path the coupler point would draw if you change the length of the bars. Let's do some spoken math to paint this picture for you to show you how sensitive this system is.
Let's set up the geometry. Imagine the coupler isn't just a straight line between the pins, but a solid, flat triangle floating in space. We will define the shape of that triangle by the lengths of its three sides, which we'll call A, B, and C. The point we're tracking is the tip of that triangle. And let's say the crank length is fixed at a constant value of 1.
Okay, so if we open the heavy Rones and Nelson Atlas, and we look at a page where the parameters are set to a specific geometry, let's say side A equals 1.5, side B equals 2.0, and side C equals 2.0. If you build that linkage, the curve drawn by the tip of the triangle might look like a very simple, elegant, sweeping arc. It almost looks like an oval that got slightly pinched on one side. Very smooth, very predictable.
But the extreme sensitivity of this system is what makes it a canvas. Small geometric changes yield radical kinetic results.
Right. Because if you flip a few pages over and you shift the physical lengths of those bars just slightly, let's say we change the triangle, so A equals 2.0, B equals 3.5, and C equals 3.5, the path completely warps. It doesn't look like a gentle oval anymore. It starts drawing these sharp teardrop shapes. One end of the loop gets incredibly pointy.
And that sharp point has physical meaning.
It does. Mechanically, that means the mechanism whips through that section of physical space incredibly rapidly, like a snapping whip before slowing down to coast on the wide, curved section of the path.
And if you push the parameters further into the extremes of the atlas,
Let's say we elongate the triangle. We pump it up so side C equals 5.0, keeping A at 4.0 and B at 4.0. The path goes completely chaotic. The point suddenly starts drawing overlapping figure eights. It loops back on itself in midair. Or if you flip to another specific page, you can find combinations that draw shapes that look like a capital letter D with a perfectly flat bottom and a curved top.
that flat bottom D shape is incredibly important. It might seem like a mathematical curiosity, but in manufacturing, it is everything.
Let's dig into that. Why is an atlas of these bizarre, ghostly curves the holy grail for mechanical engineers? How do they actually use this in the real world?
Imagine you are a mechanical engineer in 1950, long before digital robotics. You are tasked with designing an automated assembly line. You need a mechanical metal claw to reach into a dangerous pressing machine, grab a hot metal part, lift it straight up vertically to clear a barrier, carry it horizontally over that barrier, drop it down onto a conveyor belt, and then loop back around over the top to grab the next part without colliding with the machine.
You essentially need a modern robotic arm, but you have no microchips, no software, and no digital stepper motors to tell it where to go.
Exactly. You have one continuously spinning steam shaft powering the factory, and you need the complex robotic motion to be hard-coded into the physical geometry of the metal itself. Now, you couldn't easily calculate the exact lengths of the 4 bars to produce that bizarre D-shaped, straight line, then loop path from scratch. The trigonometry is far too complex to do in reverse by hand.
So you would literally sit at your drafting desk and flip through the heavy pages of the Hrones and Nelson Atlas page by page, scanning thousands of these dotted line curves. You are visually searching until you find a curve that looks exactly like the physical path you need the claw to take in real life. Straight up, across, down, and loop back.
And once you found the curve that matched your required motion, you would look at the corner of the page in the atlas. It would tell you the genetic code of that curve. It would say, to get this exact motion, you must cut your metal bars to the dimensions A equals 3.0, B equals 4.0, and C equals 4.5.
And then you just build it.
You take those numbers down to the machine shop, you cut the steel, you pin the bars together, you attach the claw to the tip of the coupler, and you turn on the single input motor. And magically, purely through geometry, the claw performs the exact, complex robotic dance you needed.
It is basically mechanical programming. You are writing complex software code, but you are writing it with lengths of solid steel. And bringing this right back to you, the listener, sitting in your car or at your desk right now, you are surrounded by 4 bar linkages. They aren't just relics of 1950s factories. Every time it rains and you push the button on an umbrella and watch that incredibly complex web of metal struts snap open, expand outward, and lock into a rigid dome that's an interwoven network of 4 bar linkages.
They're everywhere.
When you squeeze a pair of heavy vice grips and the handles close easily until they suddenly snap past that critical point and lock onto a bolt with terrifying force, that is a 4-bar linkage designed to hit a specific mathematical singularity in its curve.
Look closely at the hinge on a high-end modern laptop. Many of them don't just pivot around a single simple pin like a cheap door hinge. If they did, the thick screen would bind against the chassis when you opened it. Instead, they use a miniature, highly engineered 4-bar linkage hidden inside the metal casing.
I never even thought about that.
Yeah, when you open the lid, the screen doesn't just rotate. The linkage lifts the screen up slightly and then slides it backward to clear the edge of the keyboard deck. It's a highly tuned coupler curve living right there on your desk, allowing sleek industrial design to exist.
We have covered an incredible expanse of ground today in this deep dive. We've gone from the raw, unthinking brute force of giant Roman timbers smashing down stone walls to the playful, magical pneumatic odometers of Alexandria, through the chaotic trial and error tinkering of medieval blacksmiths, to the elegant, organized math of Rouleau's 6 atomic components, and finally to the infinite, beautiful, steel-coated curves of the 4-bar linkage. It is such a wild, twisting evolution of human ingenuity.
And looking at that historical arc leaves us with a really provocative question as we look toward the horizon. We spent the last few centuries mastering Rouleau's 6 rigid components. We know how steel and brass behave, but engineering never stops. We're currently entering an entirely new era of programmable matter and digital metamaterials.
For those who might not know, what exactly is a metamaterial in physical space?
A metamaterial is a material engineered to have physical properties that don't exist in nature. Instead of relying on the chemical composition of the metal, engineers create microscopic 3D printed lattice structures within the material itself. Because of these microscopic hinges and geometries, a solid block of this material might shrink when you stretch it, or it might change its stiffness on the fly based on an electrical current or a shift in temperature.
So it's not a machine made of parts. The material is a complex geometry, which leads to the ultimate question. What does the next fundamental building block of motion look like?
Exactly. We are approaching a point where the mechanics of the 21st and 22nd centuries might not even have distinct moving parts in the way Franz Rouleau understood them. Will the material itself become the mechanism? Imagine a commercial airplane wing that doesn't have heavy metal flaps operated by complex hydraulic linkages and I-bars. Instead, the metal lattice of the wing itself receives an electrical current, and the solid structure just bends, warps, and morphs its shape smoothly, exactly like a bird's wing altering its aerodynamics.
Wow! The boundary between machine and material might disappear completely.
It's entirely possible.
A completely new alphabet of motion, written at the molecular level. That is something to seriously think about the next time you watch a simple windshield wiper sweep across the glass. Remember, design junkies master the critical few, or the trivial many will master you. If you're leaving this episode with something you didn't arrive with, drop a comment. Takes you a few seconds, but it tells me this workbench is worth keeping open.